Welcome back to another exciting lesson for calculus. Today we're going to be talking about increasing and decreasing functions. Sorry guys, there's no one else in the classroom with me right now. I got to find some way to have a little bit of fun here. All right, so increasing and decreasing functions. We've talked about this quite a few times, so hopefully this isn't going to be brand new for you. But if we're looking at a function and we're talking about when the graph is increasing or decreasing, I'm asking you, when is the tangent positive, negative, or positive? And when we're looking at the intervals in which the function is increasing, we're writing this in interval notation. So it would be increasing from A to B or increasing from C to D. Again, I'm not worried about you using that set notation or the union notation, just making it something that you're going to see hopefully when you get further ahead into college. All right, so decreasing would be from B to C. Now, the first derivative indicates whether a function is increasing, decreasing, or neither. Again, is the tangent positive or negative? So the first derivative indicates whether a function is increasing or decreasing or neither when they meet these particular situations. So if the derivative is positive, in other words, it's greater than 0, the function is increasing. If the derivative is less than 0 or negative, then the function is decreasing. And when the function or the derivative is equal to 0, or, as we looked at yesterday, when the derivative does not exist, another way to write it is the derivative does not exist, then the function is neither increasing nor decreasing, but it may still have a local max or min. At that point. So we talked about this yesterday when we talked about Fermat's theorem. All right, so on to the first derivative test. This is what we use to identify any local maxes or mins. So C is going to be our critical number for a function, and this is a continuous function. So unlike what we did yesterday where we had a contained interval, this is a continuous function. So if f prime of x changes from positive to negative at that critical point, then f has a local maximum at C. So if we have a graph that's going from a positive to a negative, we're going to have a local maximum. If the derivative changes from negative to positive, so negative going down comes back up, then we're going to have a local minimum. If the derivative does not change sign, then f has no max or min. And so an example that you might be familiar with is a cubic function that has a point of inflection. So the derivative is going up, the derivative is still going up, but there's no actual turning point, so there's no max or min. In this case, it's called a point of inflection. All right, so we've got 3 examples to look at. The same question for every single example. It's just that we're looking at different types of functions. So it says find the intervals in which the following function is increasing and decreasing, and then identify any local maximum or minimum values. So the first thing we're going to do is take the derivative. So f prime of x is 3x squared minus 6x minus 24. We have to find our critical numbers. That means we're setting this equal to 0. So 3 times x squared minus 3 times x squared minus 2x minus 8 equals 0. So 3 times x minus 4 times x plus 2 equals 0. So x equals 4 and x equals negative 2. This is a polynomial function, so there's no restrictions. So those are our critical numbers. We then are going to find out where those points actually occur. So f at 4 is negative 78, and f of negative 2 is 30. Again, I'm trusting that you can plug those into your calculator. So 4, negative 78 is one of our critical points, and negative 2, 30 is another negative point. So from here, we're going to set up our interval, and you can do that in a couple different ways. One is to draw a number line. So essentially, we're drawing our x-axis, and we're going to have a critical point at negative 2, and we're going to have a critical point at 4. And if we were to create our intervals from here, we know that this is going from negative infinity to negative 2. This is going from negative 2 to 4. And this is going from 4 to infinity. So from there, you can pick your test points and figure out whether your derivative is increasing or decreasing. Others may choose to do this as a chart. So if you wanted to set up an interval chart, we would have our interval here. And we would go from negative infinity to negative 2. We'd go from negative 2 to 4. And we'd go from 4 to infinity. Now, because this particular example had factors, I'm going to set up the factors as part of that chart. So x minus 4 and x plus 2. Because I know that if I have a negative for the x minus 4 and a positive for the x plus 2, then I know my derivative would be negative, and a positive is negative. So whether you use your chart, interval chart, or whether you use the number line, doesn't matter, you'll still get to the same answer. So again, I'm going to save you some time just by showing you my final calculations rather than all the substitution. But if I use a test point of x equals negative 5, then negative 5 minus 4 is a negative 9, so that's going to be negative. A negative 5 plus 2 is negative 3. A negative times a negative is going to give me a positive. Negative 2, 4, I chose my test point, or sorry, negative 2, from negative 2 to 4, I chose my test point of 0. Well, 0 minus 4 is negative 4. 0 plus 2 is positive 2. Negative and a positive makes a negative. From 4 to infinity, I chose a test point of 5. 5 minus 4 is 1, so that's positive. 5 plus 2 is 7. That's positive, so it's going to be positive there as well. Looking at how that relates to our graph, from negative infinity to negative 2, the derivative is increasing. From negative 2 to 4, the derivative is decreasing. And from 4 to infinity, the derivative is increasing. So if I were to picture that, graph is going up and coming down. So this is going to have a local maximum. So local max at negative 2, 30. And the other graph here, it's going down and then coming up. So it means I'm going to have a local minimum at 4, negative 78. All right, so that's all we're doing at this point, is just identifying where the local maxes and mins are. All right, next example. It says find the intervals in which the following function is increasing and decreasing. Same question, and we're also asked to find the local max and mins. The only thing that makes this a little more challenging is the function itself. So same process, find the derivative. So f of x, or f prime of x, equals, I'm going to use the quotient rule, x minus 3 times the derivative of 2, which is 0, minus 2 times the derivative of x minus 3, which is 1, all over x minus 3 squared. Now it's important to note I have a rational function here, so I am going to have an NPV of x can't be, an NPV of x can't be 3. In other words, I'm going to have an asymptote at x equals 3. So that's going to be one of my critical points. And so if I continue to simplify here, x minus 3 times 0 is 0, negative 2 over x minus 3 squared. So I've got an asymptote at x equals 3. Let's see if we have any critical numbers. So negative 2 over x minus 3 squared equals 0. We're looking to see when f prime of x equals 0. Multiplying, we're going to have negative 2 equals 0. Well, that's not possible. So there's no critical numbers, but we do still have a critical point at our asymptote of x equals 3. So again, I'll show you both methods. We can write out a number line, Okay, so we can have our point at 3, and that would mean our interval goes from negative infinity to positive 3, or from 3 to infinity. Again, you can set this up as an interval chart, going from negative infinity to 3, and 3 to infinity. You're subbing into the derivative, okay, to see if the derivative is positive or negative. Again, I'll save you some time here. For the first one, I subbed in x equals 0. And for the second one, I subbed in x equals 5. This derivative was negative. This derivative at that interval was negative. So that means my graph is going down here and down here. And we also know that we have an asymptote here. Since the derivative is going down in both cases, we have no local max or min at x equals 3. And we know that because we also know that because we have an asymptote at that point. All right, one more example. Find the intervals, again, in which the following function is increasing and decreasing, and find the relative extrema. Now, relative extrema is the same as asking you to find your local max or min. So we've got f of x equals x to the 4th plus 1 all over x squared. You can do this in one of two ways. You could do the quotient rule. So f prime of x equals x squared times 4x cubed minus x to the 4th plus 1 times 2x all over x squared squared, which is x to the 4th. And then you can simplify 4x to the 5th minus 2x to the 5th minus 2x all over x to the 4th. Simplifies to 2x to the 5th minus 2x all over x to the 4th. You can factor out a 2x. Gives you x to the 4th minus 1 all over x to the 4th. These disappear and we're left with x cubed. So we would have 2 times x to the 4th minus 1 all over x cubed. So that's one way to do it if you want to use the quotient rule. You could have also instead said, well, I know that f of x is x to the 4th over x squared plus 1 over x squared. So you can separate them. This then becomes x squared plus x to the negative 2. And that might be a little bit easier to do the derivative of. Derivative of that would give me 2x minus 2x to the negative 3, which is 2x minus 2 over x cubed. So it doesn't matter which one you use. One just happens to be a little bit quicker than the other. Okay. For the purposes of this, I'm going to go with this one here. It's a little bit easier to work with. Okay. I might actually show you both as we go here. So for critical numbers, again, we're setting this equal to 0. If I use the first or the second one there, where I have f prime of x equal 2x minus 2x to the negative 3, or 2 over 2x minus 2 over x cubed. I've got 2x minus 2 over x cubed cannot equal 0. So I would have, I'd probably factor out 2x to the negative 3, which would leave me with x to the 4th minus 1. Can't equal 0, or sorry, equal 0. Sorry, all the way along this is equal 0. So I would have factors of x equals 0 and x to the 4th minus 1 equals 0, meaning x to the 4th equals 1. And if I take the 4th root, x equals plus or minus 1. Now, if you look back up at the top, this was also a rational function. So I would have an NPV or an asymptote at x equals 0. So x cannot equal 0, meaning I'm going to have an asymptote at x equals 0. So this one here will not be an actual critical number, but it will be a critical point. Again, you could have solved this using the other derivative as well, and you would still end up with x equals plus or minus 1. Now, if you want to draw this out as a number line, Okay, we have our critical point. We have a critical point at -1. We have an asymptote at 0, and we have another critical point at +1. So our intervals are -infinity to -1, -1 to 0, 0 to 1, and 1 to infinity. If you wanted to set this up as an interval chart, you'd have the same intervals, -infinity to -1, -1 to 0, 0 to 1, and 1 to infinity. Again, I'm using the second method that I've used for the derivative to sub in, just again because it's a little bit easier to sub in with, saving you a little bit of time. For the first one, I chose my test point at x equals -5, and that made the derivative negative, meaning the graph is going down, or the derivative is going down. I used x equals -0.5. -0.5, at that point, the graph or the derivative is positive. For the next one, I used x equals 0.5, and the derivative is negative. And from 1 to infinity, I used x equals 5, and the derivative is positive. So it's decreasing, increasing, decreasing, and increasing. So if I look at what that means, if I'm going from decreasing to increasing, that means I'm going to have a local max at -1, and subbing in, I would have had -1, 2. So here's a local max. And I have an asymptote right here, so that means there's no max or min. And then I'm decreasing and increasing. Oh, sorry, that was local min, not max. Local min, here we go. Local min at 1, 2. So local min. And again, there's no min or max at the asymptote. All right, so just to clarify, because I mixed up the wording there, we have a local minimum at -1, 2. We have an asymptote at x equals 0, so there's no min or max. And then we have a local minimum at 1, 2. All right, guys, so hopefully that gives you enough examples. If you have any questions, make sure you pop into class and ask, and have a great night.